Morning everybody. So we'll start off, it sounds like there's some confusion about capstone stuff, so just want to clear everything up and let you know kind of what the plan is and where we're at on that. So hopefully everybody read through the email I sent out yesterday closely, because that's pretty much the deal right there. So if something is not clear, probably the first place to check is there. The July 1st date is a pretty short deadline. That's maybe the less important of the deadlines. The important one is the end of July 1. Okay? If you get us a draft project plan, next week, then we have a lot more time to help you refine it and make sure that you have a project of appropriate scope and have considered the risks and tools you'll need and all that sort of stuff. So the sooner that you can send us a draft plan, the better that's going to be. It doesn't, if you aren't sure if you're even in the right ballpark, right? Send a short plan on this weekend, and we can go from there to fill in the rest of the details. In terms of projects, we have a few outstanding requests with other companies. I would not hold my breath for more sponsored projects to come in. We may get a couple more, but if you haven't seen one that you like yet, start thinking about what else you would want to do. So that could be one of the projects we've already seen. It could be a personal project. If you're not, so one of the projects, the reports I sent out in the email came about because the student was like, I have no idea what I want to do. We talked about his interests, what types of application he was interested in. We were able to find a connection because we knew it was like specifically what he wanted to work on, right? So we can still help you find sponsors, but like the projects that come from a company that says this is exactly what we want you to do, probably I'm not going to get any more of those. So I would not count on that happening. So in the very short term, like the next week or two, you should be getting at least a first draft project proposal. You can email it to me or Varun, and we'll kind of iterate on that through the month. Then hopefully by the end of July, everybody has a nice, clear, well-defined, planned out project with timelines and milestones and all that stuff. Any other questions about how that's working?
So just, unless I heard Leslie wrong, she basically told us to hold off and not panic and slow down and not worry about it, which kind of makes it difficult to know where we're supposed to actually be, because she said basically the opposite of what you and Varun are saying. And so at this stage, we're just a little, unless I heard her wrong.
So I think that's the case, because I've talked with Leslie and she and I have been on the same page on this. So I think there's a communication breakdown there somewhere.
Okay.
Panic, I agree, is not the right approach. Nobody's exactly really far behind.
But like.
But we need to move on this. It's not like a freak out if you don't have a project. It's let's make sure that we're making progress to have a project by the end of the month.
Okay, but by the end of the month, hoping to have a project, start brainstorming ideas now. That's more where we're at? Because the email made it sound like you need to whip out a project by Monday. And that was kind of...
So it's, again, the more you can help us steer you in the right direction faster, the easier it's going to be on everybody to make sure that by the end of the month you have something good. So if you wait till July 25th and you send us something and it's totally out of scope, or it's not going to work for some reason, then yeah, at that point you should panic. Right? If right now you're thinking well, I'm interested in working in this area, I'm not really sure what a good project would be, but here's some thoughts I had, and you send that to me on Monday, then we have a whole month to figure out the details. So, yeah, I'd say, by next week, should have something, some at least preliminary ideas, and then we'll make sure that we fill in the details through the rest of the month. So again, no need to panic. Right? Like nobody's way far behind or anything. We just we have a month to make sure we really nail down and have a good foundation for projects.
Yeah. I guess, I don't know, this is just a fairness in me. For the record, I don't think Nicole or like heard wrong. We spoke to Leslie last week, 2 weeks ago.
Emphasize that there would probably
Pretty
be
explicit
more.
at the time. It's possible things have changed now,
Okay.
but
Yeah, all the MSD faculty met last week, so maybe in the last, since you spoke to her, things have, the schedule has changed. So I guess that's on us for not communicating those updates.
I have a question as well. Throughout this program, I felt confident that I was going to be helped as I prepared for this project, I actually felt most of the program that there would be opportunities for, basically I didn't figure out, I'd have to figure out my project completely on my own, which I know I'm going to be able to talk to you guys and brainstorm ideas, but I really felt that there was going to be more offering in those projects.
Companies and that kind of stuff?
Companies or steering in the right direction, that's the gist of what I felt through the program. And at this stage, there's a few companies, I think maybe 3, and I have an actual project idea if I can go onto it, but at the same time, I kind of feel like I thought there was going to be more offered either through an idea bank or for me, when I look at everything, I'm still so new to programming that it's like looking in the toy store going, I don't know what I want to do, or worse, looking at some other store that's even more unknown.
Yeah.
and I was gonna say, but I was under the impression that there was going to be either more companies that come forward or that there, I guess, would be more banks. I'm not really sure what I want to do at all.
Yeah.
So if they're stuck, should we just come set up an appointment and go, I have no idea what to do?
That's totally reasonable.
Kind of ideas, or
I'm happy, any of the MSD faculty are happy to meet to help you narrow down ideas. We had some companies that we reached out to that, for whatever reason, said, okay, this year we don't have the resources to work on stuff. So yeah, a few of the projects that we kind of hoped would continue, for whatever reason, didn't materialize. Yeah, you should not feel like you're on your own. Again, if you look at Doug's project that we sent out, is a pretty good example of, this was an interest and we were able to find a really good project. So I would not panic and feel like, you have to figure it out on yourself. Cool.
Question too. I just wanted to double check on this since we asked last week, but so some of us have positions where we have non-disclosure agreements or things are confidential for that are government contract work.
Yep.
What is the process for still having a cast on related to that or for respecting that?
So we worked that out on a company by company basis. One of the reports that I was able to send to all of you was from a company that had an NDA type thing. So yeah, we can definitely work with that. It'll probably be us faculty talking with your employer to make sure that it's all above board, but you have to be able to write a report that goes to the MSD faculty. If there's NDA concerns about what's in the report, we can figure that out. And you have to give a presentation. It's not hard it has not been hard in the past to get a presentation's worth of material that is appropriate for the MSD audience that doesn't reveal important secrets or whatever. So yeah, that's just make sure you talk with us and we'll negotiate what that has to look like, but that hasn't been a problem in the past. Yeah.
So we have between you, Matthew, and Balloon as advisors, right?
Mm-hmm.
So if we're doing a project that involves maybe something that falls outside of any of your I would assume we wouldn't have an advisor outside of you guys because it'd have to be faculty, but would you guys, or do you know if other faculty are open to at least
Like mentoring or something like that.
helping out or advising?
Yeah, we can, I'm not gonna make any promises, but, last year we were able to, have some meetings with other faculty to like, help in the planning stages and stuff like that. And depending on specifically what you're working on, probably we could, faculty would be willing to meet with you during the semester to get you unstuck. Yeah, I think we can help you find some resources, but like getting, if you wanted to do network security stuff, getting Sneha to schedule a weekly meeting with you is probably not going to happen, right? But if you needed to meet once or twice through the semester, we could probably do that. Yeah, I mean, as kind of I don't know if Matthew and Varun do this the same way, but the way that I do the advising is I meet with everybody once a week. We look at progress you're making, what you're stuck on, and we try to get you unstuck. So either with whatever expertise I have, or trying to point you to somebody that knows more about whatever tool you're using or whatever problem you're trying to solve. We will definitely, help you to get resources as you need them, even if it's not my specific area. Yep.
So for those of us that are hoping to start a company, I've spoken just very briefly with my manager, and he sort of said like, oh yeah, you should, I guess, come to me with more details, more explicitly. And I don't really know what details to offer him. Your email was more helpful than what we had gotten, but still pretty open-ended.
It is open-ended, that's the nature of it. I guess, so helpful for an employer, I would think, would be just kind of the scope, say like, hey, this is like a half-time project for 3 months. Like, what's something that you think is reasonable to do in that timeline? I guess beyond that, having been in the company for a little while, hopefully you get an idea for like some of the problems they're working on, some of the things they'd like to do, and maybe you can suggest like, hey, I'd like to work on this feature. We can't really help you narrow that down too much without knowing more. So if you want, happy to talk about like, well, this is what I've been doing this summer, and these are the things the company works on, and try to come up with ideas that way. But it is, the nature of it is that it is very open-ended.
My only other question was more of a concern. So if we do commit, or we plan on doing this with the company that we're with, and then something at the last minute happens, like, will we be left high and dry because the company backed out, or we couldn't finish the project due to something on our hands or something? Or has that happened?
That has not happened. And we're gonna do our best to help make everybody successful. So, if it's August 1st and the company goes bankrupt, right, we'll figure something out. It's not, the experience we had last year is that the companies were all really supportive and helped, but if that turns out not to be the case, then, we'll have to figure something else out, and that will be harder and less ideal than, figuring stuff out in July and just going through a plan, but
We'll deal with that if it happens.
we'll deal with that if it happens. Yeah, there's no benefit to anyone if in August, like, your project is not going well for whatever reason, and we just say, sucks to be you. Right? It's not, that helps nobody, right? It sucks for you. It's not helpful for the program, right? It's in everybody's best interest to help make sure all the projects turn out well. Yep.
I don't have a question about the capstone, but I swear I saw it with due date for this next homework. Was it like July 11th instead of the 3rd?
It's different two spots, I think.
Oh,
Is it?
Can you just clarify that? Because I need to know how to like.
Yeah,
change my-
shoot, I thought I changed all those spots.
I think inside the assignment it says
Oh,
11.
it's like on the
Yeah,
screen.
like actually it's the third.
So I edited inside the assignment and it didn't get pushed. So yeah, the, we're gonna go with the 3rd because it's a shorter assignment. And
Alright.
I think,
Okay.
if you brief, yeah, I think I took like an extra day to get that pushed. But since it's a shorter assignment, it's still a full week away, so yeah, we'll stick with the 3rd. Cool. All right, cool. All right. So for putting up with all that, the reward is that today we are going to talk about neural nets. So, if you want to get a high-paying job, the next few lectures are going to be pretty important. Today we're going to talk about kind of the fundamentals. We'll look at a few examples of simple neural nets that just blow the other techniques we've seen out of the water on a few examples. We'll understand kind of where the power comes from and how they work. So, neural net is you can think of it basically as another regression technique. The idea is basically we're trying to find some function that we're trying to find some function that takes our input points and gives us the output points. And so we have a whole bunch of x and y pairs that we train on, and we're trying to figure out what function matches this. Okay. So we've seen a few examples of this. Right, what are some of the techniques we've used to try to fit an f here? Yep, so we did least squares. Right, so that was a way of finding an f that tries to match the data. Right, we could change coefficients, right? Right? And that was a way of trying to approximate a function. What else? We had categorical data. There's a few other things that we did. So in our output, our y was categorical. So we saw logistic regression. And we're trying to find an f of x. Our y's happen to be, zeros or ones, right? So we're just trying to find y equals f of x. KNN, also fitting a function. Not really a closed form solution or a way of writing it out, right? There's not like a mathematical equation you could write, but it's a function, right? Like you give me an x, I give you the y that goes with it. SVMs, right? Same deal, although there is a nice equation for it. Right? All of these are ways of trying to figure out an f that we put in an x, we get out a y, and it should match our data. So neural nets are just one more way of coming up with an f that tries to match. So, let's talk about SVMs for a second, because they're pretty powerful things. How many parameters does our model fit? Where's the two from?
Yeah, SVM,
Yeah, SVM.
the budget and the kernel function.
So the budget and the kernel function are, those are, maybe we'll call them hyperparameters or some things that we can tune. But when I fit in an SVM model, like it's solving for a bunch of numbers. And the question is, how many numbers are in there, right? If I change the number, I get a slightly different output, right, for each of those. So how many numbers am I working with? That, how many different models could I get out of that? It's kind of the question. So the SVM, basically, what we're doing is we're taking this is kind of the model we're fitting. So F is, or maybe I'll change this to a K. So this is whatever my kernel function is. This is my input point. And this is what I fit. Okay. And so basically the number of the dimension of the model that I fit, the number of numbers that I'm solving for, is basically the dimension of my problem plus 1, or plus, plus 1. So I get, the space of solutions that I can come up with my SVM is like related to the dimension of my problem plus 1. Okay. And we saw that that was like a crazy powerful thing, right? The SVMs fit decision boundaries with all sorts of wiggles and curves, and it was kind of amazing what they could do. Right? So neural networks, we can have as many parameters as we want. Right? So the dimension of my solution I get to pick. I could have 1,000,000 parameters in my solution, or 1,000, or 1,000,000,000,000. I get to pick. Right? And so it's, if I'm working with 3-dimensional data, I have my SVM, I get like four things that I can tune in my model. I can make a neural net that has 1,000,000. Okay? So the power of this function here that I'm fitting is insane. Right? I can come up with any crazy function, right? You draw me a line or whatever function you want in however many dimensions, and some neural network can approximate it. Okay? So no matter what crazy thing you're doing, we have enough flexibility in a model that we get from a neural network to match it pretty much exactly. Okay? And so that's why these things are powerful. Okay. The SVMs, we had dimension plus 1 things, variables to solve for, basically. And it could take kind of a while to train those. And we saw it for I think it was the handwritten digits. It took like a few seconds to train one of these. Okay. Neural nets, when we have orders of magnitude more things to tune, is going to be way, way, way harder to train them. Okay? So our models are huge. We have all these parameters we can tune, right? And tuning them is really hard. So training them, figuring out, okay, my F has 10,000 different coefficients to tune. If I get them all right, it's going to be like perfect on my data, right? Tuning 10,000 numbers so that I get the right output is hard to do. So that's where, so neural networks are insanely powerful in terms of what they can represent. But because there's so much flexibility, right, it's really hard to find the best parameters for the model. Okay. So these were, they started being developed in like the 60s, I guess. And in the 80s, by the 80s, people had kind of given up on them. I think because they were hard to train. How many of you are familiar with the Turing Award? What's the Turing Award?
Oh, I can't put it up right now.
It's like the Nobel Prize for computer science. The winners this year were 3 guys, at least one of which I think basically never gave up on the neural networks when they weren't cool, and has been gloating about it like a jerk ever since. And 2 other guys who I don't know quite so well. But basically, the change happened in the late, I don't know, in the mid-aughts or whatever, once we had computing resources that could actually be used to train these things efficiently. Okay. And so that was kind of the breakthrough that was like, it's kind of like interesting AI research, sort of. They don't work that well. And then like, bam, neural network for everything. So we'll talk about what these are, the building blocks, and we'll look at a few cool examples. So the main building block is called a perceptron. And these started out by as like just really crude models of nerve brain cells. Okay. So the idea is basically a nerve cell is connected to other nerve cells, okay, and it gets inputs, and depending on what those inputs are, it gets an output. Okay. So kind of the simplest thing here, so we have all these inputs. Okay. And we have an output here. And the simplest perceptron model is we take basically we give a weight to each one of these inputs. And then in the perceptron, all we do is we just add up all the inputs that are weighted by these coefficients. Okay. So maybe this input is really important, so this W is a 10, and maybe this one is not so important, so it's 0.1, right? We just add up all of our inputs with these weights, okay, and that gives us our output. So this is one perceptron. There's 2 small tweaks to this. First, we usually hook up one input to just a constant value. And the weight for that is called the bias. Right, so here we're just adding, so it doesn't matter what these inputs are, we're always just adding B to our output. And in a little bit, we'll talk about one more post-processing step we do on this guy. But this is pretty much the key idea. We have a perceptron. It takes inputs. It computes a weighted sum of the inputs, right? And this bias term, so we just add in a constant, and we get an output out. And that's a perceptron. A neural network is just the result of taking a whole bunch of these things and connecting them. Okay? So a typical way they're connected is in layers. So we start with our input layer. These are the the x's that we're predicting with. Okay? And then we might have multiple what are called hidden layers. Okay? So depending on my network, the connectivity here could be maybe it's fully connected, maybe everything's connected to everything, maybe it's not. Who knows? I might have several of these hidden layers that are connected in some sort of way. Okay. And then at the end, I'll have my output layer. So I can have as many outputs as I want, right? But somehow these are hooked up. So and so this is an example of a neural network. Okay.
Maybe I'm just being naive, but it almost seems like a little bit of this is similar to a decision tree, and I guess, is there any concern with like overfitting?
Yeah, there's a big concern of overfitting. We'll talk about training pitfalls. big concern.
What types of things are the inputs? Is it any type of thing that can be quantified or?
Yeah, so, yeah, it's basically something numeric. So if we're doing, if we have quantitative inputs, it's really easy. If we have qualitative or categorical data, might have to use like dummies or something. But yeah, it's anything that we can basically multiply by a number and scale and add.
Is the B consistent through the whole network?
No, so each perceptron gets its own bias.
Why is that necessary, or like how is that added?
So it's necessary because if we would like to be able to still have some output even if all the inputs are 0. That's useful. That's the idea. So even if all the inputs are 0, we still want something. So this is an example of a feed-forward network. And it's called that because everything just goes from left to right. I don't have any like loops going back or anything crazy like that. Right? So if I want to do a prediction with this, right? I just set the values of my input layer, and I just run it. Right? Each one of these, I just compute the sum of the things from the previous layer, and then just follow that through till I get to the end. So I can process this layer by layer. So, as I have drawn this is actually just a really complicated way of writing out linear regression. So my perceptron, all I'm doing is I'm taking weighted sums of the inputs and adding them together. So actually what I get at the end is just a weighted sum of the inputs, where the weights are some complicated function of all the weights through here, but it's just going to be a weighted sum of all of my inputs. And so what I have described here is actually just a really complicated way of expressing linear regression, which is somewhat unsatisfying and not super useful.
So will it still be linear? I mean, we have multi.
It will be linear because my inputs are never like multiplied together or never have anything else happen to them. I'm only scaling my inputs and adding them. And that's all I'm ever doing.
For the NAT structure, where we could have different inputs from different inputs.
So what I'm going to get at the end is so I'm going to have just a weighted sum of my inputs. The A, B, and C here are going to be some really complicated thing depending on how everything is connected, but it's going to be a function that looks like this, which means I'm fitting a plane, basically. So the model here, despite looking really complicated, is just a really complicated way of writing linear regression. So not great, right? Basically totally useless. This is a slow way of doing linear regression. The trick key here is after we add up all the inputs, we run this through a nonlinear function. So we do something to this weighted sum to give us a something at the end that is a nonlinear thing. And this is basically how the magic all works. So there's a few different choices of f that we might pick. So kind of the first one, which was based on a really crude model of biological neurons, is a step function. Right. So basically what we do here is we turn the output on or off, depending on the inputs. And it's either off or on. Okay. The bias you can think of, this B, you can think of as figuring out where it turns on or where it turns off. Right, and the weights kind of determine, which inputs are more likely to turn it on or whatever. So this is, people don't really use this, but you know, it's kind of one of the first functions here. This is called an activation function. So it takes the weighted sum of my inputs and does something to that before, and that's the output of my neuron. Okay. So this is the step function. We'll talk about why. Maybe we'll talk about how we train these, and we'll see why this is a really bad choice. So, any guesses how we go about training one of these? So first off, what does it mean to train a neural network? What is it that we're trying to figure out?
Change the weights.
Exactly. So what we're trying to do is we're trying to figure out what the best weights for each neuron are. And that's what it means to train a network. It means to figure out, okay, each one of these connections has a weight associated with it. What should those weights be? And what is the goal of our training? Like, how do we know if we've chosen good weights? Yeah, the outputs, the predictive outputs that I get should match the input labels or values that I'm given in my training data. So we're trying to pick the best weights to match so that our predicted values of y are the same as the given values of y. So any thoughts on how we do that? Yeah, it's basically guess and check. So what we do is we start out with some random guesses that are weights. So we can measure the error. We can see how good these particular weights are doing, right? And then we somehow have to come up with a way of improving them. Right? So I have some weights. I know how good or bad they are. And somehow I have to figure out how to change them so that hopefully they get better. And to do that, we're going to use calculus, and specifically vector calculus, which still scares me a little bit. So the idea is, let's look at just this weight right here. So I'm looking at the weight for this connection. I want to change this a little bit so that the error that I get at the end decreases. So I need to know how the error will change if I change this weight a little bit. Okay. Those of you that remember calculus, what am I describing here? I'm going to find out how one thing changes as another thing changes. This is a derivative. Yep. So what I'm interested in finding is the derivative of my error with respect to my particular weight. So this tells me how does my error change if I change the weight a little bit. Okay. And so if I see this, right, I can reduce my error a little bit by going in the opposite direction of this. Okay, so the opposite direction of this is the direction that will reduce the error. Right, so I change my weight a little bit in that direction. That kind of makes sense. Right, and this is something I can compute easily. Okay. Right. So that's the idea. And I could do this one weight at a time. That turns out to be really bad for a number of reasons. So actually what I do is I compute basically the derivative of the error, the change in the error, with respect to all of the weights at the same time. And that tells me basically how I change all of my weights just a little bit to reduce the error. So the way that's helpful is like some weights are going to be more sensitive than others, right? So some weights I want to change a lot, some weights I want to change a little bit, some weights I want to increase, some weights I want to decrease, right? So by looking at all of them at once, it's actually way, way, way more effective than trying to go look at each one at a time. Okay. So So I'll draw a 2D picture. So if I just have, so in this case, I have a single weight. Okay. I'm looking at one weight, and I'm plotting my error. Okay. If I'm at a particular spot, I basically want to go in the direction that decreases the error. I want to like go right a little bit. Okay. And so the derivative information, the derivative tells me, hey, like, you should go a little bit to the right. And I'm saying, okay, I'm going to go here. And it says, okay, well, you should go a little bit to the right. Okay, well, you should go a little bit to the right. Okay. And if I do this enough times, eventually I'm going to get to the minimum error, and I'm going to hopefully have a good number. So that is that's the kind of the key idea of how I train these networks. When I compute all of the derivatives at once, that's called the gradient. So that's the gradient is the basically how each weight should change to change the error. Okay. And this process of going downhill is called gradient descent. Okay. And so I just use a little bit of calculus to roll down this hill till I get to the bottom. Question?
So when you say you're finding the overall error, this has to be over like a whole test set. So you test like 100 different things. You say I got 2 of them right.
So I could describe it one at a time, or I could talk about a bunch at a time, and we'll talk about that in a second.
Oh, or maybe you'll talk about it. But if you're doing 1 point at a time, how, if it's like this is right or wrong, how do you measure you've gotten like closer to right?
Yeah. So for the say we're doing classification, okay. I would want to design my output so that I don't output true or false. I output a probability of true. Okay. And that way I can say, oh, if I'm like 95% sure it's true and it's true, like I'm doing pretty good. If I'm 95% sure it's true and it's false, then I'm not doing so good. So that gives me a smoother way to measure that. Including a bunch of data at once is also helpful.
So the output is usually quantitative, it's not like a KNN.
Yes. So when we do predictions, we usually so one way we could do it if we have like a multi-class classifier. So like the iris data set, we have 3 outputs. We could have like an output for each type of iris, and we would like look at the max of those 3 or something like that. So we might do like a little bit of post-processing on the output there.
This gradient descent, aren't you gonna get like trapped if you have data that has like multiple waves up and down?
So you are describing
Yeah.
local minima.
Yeah.
Yep. And yep, you get stuck in local minima.
Is there a way to solve that?
Yeah.
Not really.
So there's a few things. So we'll talk about that in a second. So now that we kind of know how we train these, we can actually see why this is a really bad choice. Because the calculus works for little itty bitty changes over very small distances. If I'm kind of in this range, my output, and I change my input just a little bit, I'm going to have a huge change in output. Right? The derivative here is infinity. And that kind of just screws everything up. Okay. So when I have sharp things in here, the derivatives are infinite. So if I plot the derivative of this function, here it's going to be 0. Here it's going to be infinity. Here it's going to be 0. Right? So if I'm trying to use this as information for how to change my weights, it's useless. It tells me, if I'm over here, it says change your weights all you want, it doesn't matter. If you're here, it says change your weights all you want, it doesn't matter. If I'm right here, it says if you touch your weight, infinity, right? So it's totally useless, right? So this function is basically, impractical to train. Okay? So step function, just because of how we have to figure out these weights, step function sucks. So people still like the idea of the step function, like this on or off kind of thing, but they wanted to actually be able to train it. All right. Which function have we looked at that is a smooth version of this? Sigmoid function, logistic function. Okay. So another activation function that used to be really popular is the logistic function. Okay. And there's another one that's very closely related called the tanh, or the hyperbolic tangent function. These are both basically smooth versions of the step function. Okay. So they have similar kind of behavior, but there's actually a derivative here. So that's pretty useful. Okay. All right. So these were like the go-tos for a long time. So people would use a sigmoid function for f. And the modern machine learning folks have figured out that actually the one that works really well is called the rectified linear unit, which is, it seems like a really dumb thing to do, but it works really well. Basically, all I do is f of x equals x, so I don't change my output, except if it's negative, I just clamp it to 0. So the way this looks, if I have positive, I just output my weighted sum. If I'm negative, I just output 0. The reason this is an improvement for both of these smooth step functions, if I'm pretty far away from this transition point, my derivative is 0. It's like basically flat, so it's like hard to. If I do gradient descent, I just like go really slowly because it's not very steep, and so that's a problem with this ReLU. My derivative out here is steeper, so I get, it's more useful. We have the same problem here of the negative having no derivative, but I guess it's okay. There's this kink here where it changes. Again, you would think that would be a problem for a calculus perspective, but it seems to not be. So this ReLU is kind of the typical activation function. When we put this in here, we basically just clamp the negative values to 0. That lets us represent all sorts of crazy functions in the output, and it's relatively easy to train, and that seems to be kind of the most popular activation function. So that's a neural network. We have these perceptrons. We take inputs, we multiply them by weights and add them up. We run it through an activation function, and we just do this thousands or millions of times, and we get numbers out of our output layer, right? And that's our predictor. When we train these, what we do is we just take our input data, we run it through, we look at the error, we look at the derivative of that error with respect to our weights, and then we change our weights slightly to reduce the error a little bit, and then we just repeat that until we minimize the error. So that's the idea here. Questions on that kind of general idea?
Can you repeat one more time about the activation function there? That part.
So we need to put something, we need to process the output of our neuron so that we can output complicated functions at the end. So if we don't do this, then we're just doing complicated linear regression. If we mess with the output of each neuron somehow, the cumulative effect is that we can match interesting functions at the other end. And so basically anything that's nonlinear, that smushes it or kinks it or bends it or whatever is a possible candidate. The ones that are popular are either the smooth step functions or this ReLU, where we just clamp the negative values to 0.
It's like a rectified linear function, but end up being linear regression in a lot of cases.
Because we have a bunch of stuff that's going to be in this region, it's not.
I guess, how do you know your bunch of stuff is, I mean, if all your inputs are positive, it's just a weighted sum.
So you'll have negative weights, probably. Okay. So the inputs and the weights can be positive or negative. And it's, once you go one level in, right, you're going to get all sorts of crazy stuff. Yeah, yeah, this works really well in practice. Yeah.
And does this go layer by layer, or is it?
So we just, so to compute the output of a neuron, we have to know what came ahead of it, right? So we can compute each neuron in a layer we can deal with independently, and then the layers we can deal sequentially.
I guess, would the weights ever get more negative with that function then? Like, how does that work? So with our, like, your simple example, where you're looking at one perceptron, you're kind of shifting towards that network, right?
So thinking about it in terms of one is probably not that helpful for intuition, because these are interesting and work well because there's so many of them. It's the huge interconnected nature that makes it work. Yeah, that's basically the way that we add a bunch of complicated things together or add a bunch of simple things together is kind of the magic that makes it work. All right, so this is the key idea. So if we want to use a neural network for solving a problem, there's a few things we have to do. First off, we have to pick what our network's going to look like. Okay? So basically, how big are our hidden layers and how many of them are there? And we'll talk about different types of layers that we have either tomorrow or next week. So that's one challenge is, okay, what is the right shape of our network? Another challenge is deciding on our activation function. So do we want a ReLU or do we want a sigmoid, basically? And then the third challenge is figuring out how to train it. Okay? So basically all of the training methods are some sort of gradient descent based thing. To get around these little valleys, we can add some randomness. So we compute the gradient from calculus, then we add some noise and see what happens, right? So if we're stuck in a bad spot, the noise might get us out. There's another technique called momentum, where we kind of remember which direction we've been going in, and we keep going in that direction. That can help like roll us out of little valleys and stuff like that too. We could use more calculus. We can use second derivative information to help optimize faster, but basically it's this gradient descent with some tweaks to improve it. Right. And so that's basically the gist. So as we're training, we pick that stuff, and then to train, so we pick basically what our optimizer is, so how we're gonna try to find the best weights, and then we pick two parameters related to how we run data through, and these are the batch size and the number of epochs. Okay. So as Eric hinted at, trying to train this on one example at a time is going to be like pretty noisy. Okay. So usually we take our data, we split it up into a bunch of batches. So I'd like 256 examples at a time, for example, and we run each batch through. We compute the sort of total error for the batch, and we update and repeat. Okay. Once we get through all of the batches one time, that's called an epoch. So an epoch means we've seen each of our training samples one time, right? but we do a weight update per batch. So as we train, that's what we'll do. Okay. So let's take a look at some examples. To start with, we're going to look at a cool online demo from Google, the TensorFlow people. So here is an example of a neural network. So if you guys playground.tensorflow.org if you want to play along. So we get to pick our activation functions, and maybe we'll use the ReLU function. The learning rate is related to our optimization. So when we're trying to find the best weights, this basically says we do calculus to figure out how we should adjust the weights, like which direction, and then the learning rate says how much should we adjust them. So it's basically the scale for the direction. There we go. The regularization is an extra thing we can add. So usually having really big weights is a bad idea. So we can control that here. And yeah, so we're going to look at the classification problems. Here we have, these are our data points. We can split our training testing data. And here's our batch size of 10. So we're going to look at 10 data points at a time as we're training. So if I just run this, so here basically the inputs that I have are X and Y. So my input layer is just the X and the Y of my data point. And the output I'm trying to classify, whether it's a blue or an orange point. So maybe we'll start with 0 hidden layers. Do we think this is going to work at all? All right, so if we look at the X and Y, and we try to figure out the, in the circle, right, that's not going to work at all. So we train this, we'll get something, but it doesn't, so our loss is our error. Our error is like basically 50%. So we're flipping a coin. Not very good. If I change my my features, my inputs, so if I look at x squared and y squared instead of just x and y, do we think this is going to work better? So what's the equation of a circle? So x squared plus y squared equals the radius squared. So actually here we have a hope. We have a hope of this working because we can just kind of compare this, and indeed, with these features, no hidden layers, works like a charm. So an important part of this, maybe less so now, but historically it was a big deal, was coming up with good features for your data, because if you pick the right features, your network can be pretty dumb, and you can get good outputs. With the modern approach is what we call deep learning, where we have a bunch of hidden layers, and basically the first few hidden layers kind of learn good features. So if you look at the outputs of the first couple of layers, you'll actually see they kind of look like features we might try to design ourselves. Okay. So we'll add one hidden layer. Let's go 4. We'll add 4 neurons here. Okay. So again, we just stuck one layer in between our input and our output. and it works pretty well. So we look at the layers. Basically, each of these layers can only fit kind of a linear divider, a linear separator, because it's still like a line shape. And so each one of these, we're just finding some line. Okay. And when we add them all up, we actually get something that works pretty well. So we added a hidden layer, and it worked pretty well. If I add a few more neurons here, what we can see, so the colors tell us basically what the weights are. We can see that this neuron here isn't doing a whole lot. It's not very helpful, or the weight is really small. So 8 is probably more than we need here. So maybe let's pop that down. Oops. This one also not that useful. So maybe 7's too many. So here it looks like with 6 neurons, we're doing really great. So, right, so we have a simple neural net with a one hidden layer, right? Each one of these is fitting something really simple, and when you combine them, it works really well. So let's take a look at a more complicated example. So this is call this the jelly roll. Okay. So again, we run this, and we're training, right? We're kind of doing a little bit better, but not that well. If you look at the curves, so we have the training loss is the lower curve, and the testing loss is the higher one. So we're doing pretty good on the training data, but pretty awful on the test data. So this one basically, we're trying to add up a bunch of planes to get this spiral shape, and it just doesn't work. Right. So the solution to this, with all machine learning problems, is add more layers. So we're adding 2 neurons basically, but we're splitting them into different layers. Right? So I'm just going to have 2 layers of 4. Okay. Let's see how we do. We're doing better than we did before. And it looks like still not great. Oh, a little better. Pretty big improvement. So it's still not perfect, right? But let's look at the second layer. Since it's a combination of the layer before it, we're actually starting to get more interesting shapes. So here, right, we have this kind of, almost curved shape, right? So, like, by adding another layer, each layer can represent more and more complicated functions, right? And the output is going to be the most complicated function of all. So let's add one more layer. So I've added another layer, right? The training is probably going to take a little bit longer because I have more weights to try to figure out. But let's see how we're doing here. And, slightly better. If we look at what we're fitting here, we have kind of the top piece, right? So we've captured the top part of the circle here. Here we're kind of trying to capture some weird stuff in the middle. Let's add maybe just a little bit more, a few more neurons here. And now we're starting to get somewhere. Right? We're starting to get this, actually get the internal spiral shape. So now, if we look at our training loss and our testing loss, right, we're starting to nail these predictions. It took a long time to train. It took almost 1,000 epochs. right? But, right, we're actually capturing this really complicated function with just 3 layers. We have 15 neurons, that's it. So we add one more layer. So we add one more layer. What do we get here? So we're having trouble training this. And if you look at the things, our weights are pretty big, the lines are pretty thick. So we're going to add one more piece, although we're starting to get it, which is regularization. So this basically is a penalty against having really big weights. So as we're training, we want to keep our weights relatively small. Let's try this. We'll add that. So this should help with our training a little bit. Maybe. There we go. It'll improve over time as I go through more, but I'm impatient. We'll just bump up the neurons a little bit in each layer. And now we should be able to capture all sorts of interesting features as we go through here.
Sorry, I kind of missed, what is that regularization rate?
So it is basically how much I penalize big weights. So this is saying I want my weights to be small, but this is like the least amount of, this is like the smallest penalty for big weights out of.
So by penalizing the big weight, are we adding, I don't know, the bias or?
It's basically changing how I compute the gradient. So if I'm going to change my weights to make some of them really big, I'm actually not going to, I'm going to kind of adjust my gradient so I don't end up producing big weights. Yeah. Cool. So I think I can do 5 layers. So I'm kind of stuck in my optimization. Nothing's changing. So one thing I can do is I can add a little bit of noise. See that? So I might be stuck in the local minima right now with the noise. That's going to get me out of there, and my training continues. So as you've seen, like as we add more layers, it kind of gets harder. The training part gets harder, right? Because there's way more weights to fill. The gradients are going to be weird. But that, if it ever becomes stable, that's really good. I think it's pretty sensitive to the noise here, but doing a pretty good job. Yeah.
So I did 2 different layers of 6 neurons each, and got a 0.024, which I think is as good as you've gotten or better. Is that just lucky there, or like how does that? I guess how do you determine when you want to add more nodes in a layer or add another layer?
Yeah, that's kind of like experience and intuition being a practitioner, I think. So learning how to design appropriate networks is kind of, I don't think there's an easy answer to that. Okay. So I encourage you to play with this. It's pretty fun. It gives you kind of intuition for what these various things do. So maybe we've been playing with the ReLU. Let's try to play with the sigmoid and see if that changes anything. Yep.
Sorry, I'm still kind of confused about why do we want to avoid choosing very big parameters? Like if we have very large omega I, maybe that just means the input I is not repeated.
Yeah, so that can make it pretty sensitive to noise. Having big weights can make noise extra bad. So that's one reason. So it looks like for this one, the sigmoid is not a good choice. That's pretty bad here. Cool. So this is the TensorFlow playground. It's pretty fun. Let's take a look at some scikit-learn stuff just to see how this performs on our usual suspect data sets. So this is a picture of a perceptron. So basically, we just take all of our weighted inputs, sum them up, run them through the function, and that's our output. Here are some shapes. So depending on your task, some of these shapes might be important or not. We will look at convolutional neural networks. And maybe a couple others in here. Autoencoders we'll look at as well. There's a whole bunch of different libraries. We're going to play around with Keras, which is a pretty nice Python API that can use the TensorFlow backend to be fast. Raw TensorFlow is unpleasant to work with. Okay. So here we have the 2Moons data set. So machine learning is pretty sensitive to the scale of the data. So these neural networks are really sensitive. We're actually going to scale things to be like 0 to 1. That's what the standard scaler is doing. Yeah. So yeah, the training just gets a lot harder at different scales for whatever reason. So scaling can help you with your training. Right, so here's our 2Moons. We've seen this a bunch of times. Right. We're going to use the scikit-learn. So the MLP stands for multi-layer perceptron. So this is just a neural network with multiple layers. We're going to have 3 hidden layers with 3 neurons each. Yeah. We're going to use this atom solver. So this is a modified gradient descent solver. So it's and it works really well. So it has some tricks to avoid local minima and that kind of stuff. And yeah. So if we fit this, you can see our loss that we start out with is pretty high. So we're like getting the right answer half the time. Not so good, but it really quickly goes down, and by the end we're at about 10%. So we're getting 90% accuracy more or less. And then the solver, basically once we stop improving, basically we just say, okay, so these are the ways we're going to use. So, and actually if you look, you'll see that we got better, and then we actually got worse for a few iterations. So the optimization, it's a hard optimization problem. If we look at the plot that we get, this is what we fit, right? If, from what we saw in the TensorFlow stuff, this kind of makes sense, right? Where our first layer is just fitting lines, and then our next layer is adding the lines up, and our third layer is adding those lines up, so we get something that kind of looks like the addition of a few of these planes put together. So it works on that data set. Some stuff we can find out about the model is the shapes of our output. So our first layer, our input layer, has 2 inputs, right? The x and y of the points, and 3 outputs, because each of our outputs is connected to one of the nodes of our hidden layer. And our 2 hidden layers are both 3 by 3. So we have 3 inputs and 3 outputs. And our output layers, we just have a single output value. And these are what the weights happen to be. Occasionally, the weights can tell us interesting things. So we're doing stuff with like images. The weights can actually kind of, if we visualize them as an image, kind of tells us cool stuff about like the shapes that it's recognized and that kind of stuff. Yeah. So these are the activation functions we talked about. So the step, logistic function, TANH, which is again, so these are both just smooth steps, and then the ReLU, which is just flat, and then just f of x equals x. If we look at the derivatives of these, right, the derivative of the ReLU is 1 when it's on, which is like a nice, good number, and it's 0 when it's kind of off. And then the other ones have kind of these smooth shapes, but far away from 0. The derivatives are 0, so they don't. It's hard to train them. They don't move very much. When we talk about neural networks, we talk about loss functions a lot. The loss function is just how we measure the error. So this, when we did least squared, the loss function was just the sum of squared errors. This alpha term here is the regularizer. So this was basically, there's a penalty for having big weights. So if the weights are big, then it's a bad network. So we want to avoid that. So that's kind of the idea. This is just showing a bunch of the different parameters that we can pick for all these different options. So here we have, we're running the same network with different solvers and different parameters on a whole bunch of, on 4 data sets. The important thing I would show you is that the Atom solver is the fastest to reduce the loss in pretty much all of these. So the Atom solver works really well. Cool. So we have, so there's a few data sets. So one we'll look at is predicting whether breast cancer or whether tumors are cancerous or benign. So we have a bunch of information about tumors. So we have the radius of the size, some measure of texture. So just all these various features. Okay? And we're trying to predict, is it malignant or benign? Okay. I don't know very much about this data set, but we are going to train a network with 3 hidden layers. Okay. And if we train this and perform predictions, we nail it, right? That's like, so we only misclassified 3 examples, right, out of over 100, right? That's like, these are good classifiers, or can be. Right, so yeah, we didn't really know much about the data set, and we were able to get really high accuracy. Okay. The digits, so this is the handwritten digits. This is actually a larger version of the data set that we've been using. Because we have so many weights to tune, we need a lot of data to make sure that we're not overfitting and all that stuff. This is like a bigger version of the digits data set. We're going to have 2 hidden layers of 100 nodes each. So we're training a lot of weights, right? So for the first, from the input layer to the first hidden layer, we have 100 nodes times however many inputs, so maybe 64. If these are still the 8x8 pixel ones, then we have 6,400 weights in that next layer, in that first layer. The second layer, we have 10,000 weights. We have 100 connections from the first layer to each of 100 nodes in the second. We have 100 squared, so that's 10,000 weights for that layer. And then the output layer is going to be, we're going to have 1 output for each digit. So we'll have a 0 output, a 1 output, a 2 output, right? So we have another 1,000 layers. We have 100 hidden layer things, each connected to 10 of the outputs, right? So here we have like 20,000 weights that we're training. Okay. So it can be kind of slow. We see that we quickly improve our accuracy. And at the end, again, we are nailing it. We look at the accuracy on this data set. We are, looks like our 9s are a little bit hard to do, but we're still like 90-some% accuracy for each one of these, right? We're, I think this is way better than any of the other algorithms we saw. And it makes sense because this is a much more complicated model, right? We have 20,000 parameters we can tweak, whereas with k-means clustering, we had like 640. Right? So these are much more powerful models if we train them well. And then we have one more. This is kind of like the second homework we did with the housing data. So we have all this information about our neighborhood, and we're trying to predict the median house value in that neighborhood for some reason. Again, we will, so we'll look at just a linear regression. So we're going to throw all of our features into a linear regression and see how well we do. And we get like, I think this is the R-squared value of like 0.6. So not that great. We're explaining like 60% of the variation. Not that great. We use a neural network with 2 hidden layers. There are only 8 nodes in each layer. This is like we could have run this in the browser. Right? And we get like 75% R-squared-ish type value. So this is a pretty simple network, and yeah, big boost. If we just to show the importance of the activation function. So the activation function of the identity means like we don't apply an activation function. It's just nothing. And if we look at what we get from solving this with the identity, it is exactly the same thing we got from linear regression. So without an activation function, this really is just a complicated version of linear regression. So the activation function is important. Yep. So yeah, that's kind of an intro to neural networks. Right. The key idea is we have these perceptrons or neurons with activation functions. We just hook them up together. We optimize to find the best weights, and if we do that well, these are very powerful models. Any other questions? I encourage you to play around with the TensorFlow playground. It's pretty fun and gives you good intuition for how that stuff works. Cool. See you all tomorrow.